agents that can see, hear, and interact with the physical world. They can write code, analyze data, and execute precise movements. But physical capability is no longer the engineering bottleneck. The real danger is what happens when these systems execute unguided, autonomous decisions in high-stakes environments. That brings us to agent number 22, the ethical reasoning agent. This is the first component of the governance tier, and unlike every other system we've built to take action, this agent is engineered specifically to say no. Right now, the industry relies on a dangerous anti-pattern. Engineering teams try to make systems safe by taking an LLM toxicity filter and bolting it on to the very end of an output pipeline. A natural language prompt telling a model to do no harm falls apart at runtime. When an agent is orchestrating a complex, multi-step sequence of API calls, a simple text filter at the finish line cannot catch the logic errors happening mid-process. Think of the filter model like a leaky pipe. Data slips out the end before the system can react. To prevent real damage, you need a vault door that drops down immediately before an external API call is ever made. Preventing real-world harm requires a deterministic architectural gate embedded deep inside the execution loop, not a post-hoc band-aid slapped over the final text output. To understand what happens without that gate, look at Amazon's AI recruiting tool from 2018. It did exactly what it was trained to do. It was faithfully reproducing patterns hidden inside a decade of historical hiring data that severely penalized women's resumes. These tools are deployed into massive corporate structures, running silently in the background, making thousands of decisions before anyone realizes the outputs are skewed, and the project has to be quietly scrapped. But that was merely a static model. We are now deploying adaptive agents, which operate under what we call the dual exposure model. A biased model is like a bad photograph, frozen in time. An adaptive agent is like two mirrors facing each other. Every skewed decision becomes training data for the next cycle. Historical inequalities bounce back and forth, compounding superlinearly. Because this agentic bias feeds on itself, the architecture must aggressively intercept the decision before the action can taint the environment. This brings us to the tension of the pre-execution checkpoint. A standard reasoning engine looks at a goal and asks, "Can I do this?" Agent 22 interrupts and asks, "May I?" You cannot answer that question reliably with ambiguous natural language policies. Balance efficiency with safety is a phrase a human understands, but a machine interprets differently every time. To translate "may I" into a machine executable format, we use Deontic logic. This is a specialized branch of modal logic concerned strictly with permissions and obligations. Under this framework, every proposed action is assigned one of three strict modal operators. It is obligatory, meaning the agent must do it. It is permitted, meaning the agent may do it. Or it is forbidden, meaning the agent must not do it. Before any execution happens, the proposed action is tested against an active ethical rule set to check for logical consistency. This relies on the ethical consistency theorem. An action is granted permission to execute if and only if adding it to the current rule set introduces zero logical contradictions. Deontic logic strips away abstract philosophy. It replaces vague corporate guidelines with a hard mathematical barrier that the agent is structurally incapable of bypassing. Let's trace the actual pipeline. This schematic maps the entire pre-execution loop. It starts on the left, where the standard reasoning engine formulates a plan and proposes a candidate action. Instead of executing, that action hits the ethical checkpoint. It is forcefully intercepted before it can touch the outside world. Inside this checkpoint are modular validators aligned with IEEE frameworks. Crucially, these are deterministic rule lookups. They are not unpredictable LLM calls. The action then moves into the Deontic consistency block, where the system runs the logic test to assign its formal moral status. The consequence is binary. If the proposed action creates a contradiction and is deemed forbidden, the system halts the execution thread. But a blocked action doesn't cause a system crash. The architecture routes the failure down into a dedicated mitigation pathway. The system applies automated rules to modify and sanitize the action, like stripping out personally identifiable information, and then loops it back to revalidate the modified version against the rule set. If an action absolutely cannot be brought into compliance, the final failsafe triggers. The action is entirely blocked and escalated to a human operator for review. This architecture actively shapes and corrects behavior in real time, creating a resilient safety net rather than a fragile fail state. Once an action passes the consistency check, it reaches the final dispatch phase, where it is released into the environment. Notice where this sits in the pipeline. The gate is bound strictly to the tool interface. It monitors the actual API executions, not the final conversational text output. But the system doesn't stop evaluating once the tool runs. It feeds the results into the bias monitor, treating fairness as a continuous service-level objective, operating exactly like server uptime or latency. This streaming pipeline tracks aggregate outcomes over a sliding window. If the disparate impact ratio drops below a legal threshold, like the EEOC's 5/4 rule, the system instantly fires a critical alarm. This forces us to confront the impossibility theorem. In the formal study of fairness, achieving perfect statistical parity, equal opportunity, and predictive parity all at once is a mathematical impossibility when base rates differ across groups. The architecture doesn't magically solve fairness. Instead, it forces engineering teams to make explicit, auditable moral choices about which fairness regime they prioritize in production. To prove this architecture works, we have to look at the Python implementation from Chapter 12. Inside this core Python class, ethical principles are hard-coded as strict modular objects, not fluid prompts. Every proposed action runs the gauntlet of the evaluate action method. If an automated fix fails, the mitigate method triggers an escalation pathway to a human. This specific code structure transforms a vague corporate do-no-harm policy into a strictly enforced compile time requirement. In high-stakes environments, executing hiring screens, approving financial loans, or making medical recommendations, every single decision must be legally and morally defensible. But the system has a strict limitation. The agent enforces values. It does not invent them. The burden of choosing the correct moral regime remains entirely on the human engineer. Agent 22 is the gateway to the true governance tier. It establishes the absolute boundary between an agent's capability and a human's control. But if our system is going to automatically block or modify actions in the real world, it must be able to mathematically explain why it intervened to a human auditor. That requires building the other half of this governance equation, Agent 23. Review the complete Deontic logic framework and full code repository in 30 agents every AI engineer must build, and access the curriculum at neuralsca.